All right, so if we look at these things real quick here, doesn't this make sense? The sum law for limits. If I have the limit of the quantity f of x plus g of x as x approaches a, what can I do to that? Simple. I can just break it into separate limits, right? So in other words, I can evaluate the limit term by term. I can evaluate the first term separately from the second. Okay? And if, for example, we define the limit of f of x as x approaches a as having a value L, right? That's equal to L, some number L, and the limit of g of x as x approaches a just equals some number M, then all we have to do is evaluate those separately, and our answer is L plus M. Big deal. It's exactly what your intuition would tell you to do, right? Same thing for difference law. Those are interchangeable, right, essentially. Constant multiple, this is a big one, but it makes sense. If I'm going to take the limit of some constant times f of x as x approaches a, then what I'm able to do here, and in math the words we would use are really simple. We would extract the constant out front or pull the constant out front. I can pull it out in front of the limit, and so c is just multiplied by the limit. So the answer is just c times L, right? Okay, so I can, in a sense, I can factor the constant out of the limit, pull it out front. Okay? Product law, what do you think happens if you take the limit of f of x times g of x? Break them apart. The limit of f of x times the limit of g of x. So your answer is just L times M, right? Quotient, same thing. Power law, same thing. If I have the limit of f of x to the power n, then I could say, well, I could say that's the same thing as the limit of f of x, that quantity, to the power n. So I can evaluate the limit first, and then, whatever the answer is, take it to the nth power. Okay? Same thing for roots. So it's really no big deal. Oops. Like here's a quick few examples. And in this textbook, one nice thing they do is they allow you to like try stuff and then check the answer. Right? You'll get plenty of practice, additional practice in assignments, but that's kind of nice. So what would you do with this if I had the limit of 4x plus 2? Well, technically, that's a sum, isn't it? Right? The limit of 4x is just, I'm going to let negative 3 solve by substitution, and the limit of 2 is just 2, right? The limit of a constant is always just equal to the limit, and that's given to us up here at the beginning, right here. If c is a constant, the limit of c as x approaches a is just c. Why is that the case? Let's take one quick look at that one. What does the function f of x equals c look like if c is a constant? Straight line, isn't it, right? So we get something like, if that's c, then the function just looks like that, doesn't it? Right? So if I've got some value a that x is approaching, as the ant approaches a from either side, what y value does the ant obviously have to approach? C. Because his value is always c, isn't it? Right? Okay. So you've got those properties of limits, limits of polynomials. One byproduct of that is a polynomial is just a sum of terms, right? So if I'm going to take the limit of a polynomial, what do? Just evaluate it term by term. Just break it up into a bunch of smaller, simpler limits, right? Or a rational function is a ratio of polynomials. Same thing, right? Break it up term by term, okay? So for example, how would I evaluate the limit of this rational function? I would just take the limit of the top, right? Get an answer. Limit of the bottom, that's my answer. That's that ratio. Okay? Just what you'd expect to do. Is this anything new? No. This is the same stuff we've already been doing, just because it's so intuitive. Okay? So you can see why we don't really spend a lot of time on that. It's just totally intuitive. Okay, but what I do want to do, so I do want to push things one step further with evaluating limits analytically. Let's go back and review what we did last Friday, most recently. I'm going to give you a problem, and you try this while I take roll. So how about, do those two for me, how about? We're not totally done yet, but let's go ahead and talk about these. How about that first one? What are we going to do there? Okay. You could, yeah. Okay. You could, but you don't really need to in this case, do you? We can just evaluate this one directly, right? Remember, that's always our first option, is we'll attempt to evaluate it directly. One of three things are going to happen when we evaluate directly. Do you remember what those are? Either we're going to, what? Get an answer, and we're done. We're going to get some rational answer, or irrational, I guess. We're going to get some answer, that's it. That's the answer. Or, what else could happen? Could get no limit. If we get a number on the top, but a 0 on the bottom, that's no limit, right? We'll talk about what else we could maybe do with that. We're going to talk about the topic of how do we deal with infinite limits more precisely here very shortly. But for now, we'll just say no limit, and that's fine. Or, what's the other possibility? It's an indeterminate form, yeah. 0 over 0, which means more work. There's some other indeterminate forms also, which we won't deal with for now. We'll get to eventually. Like, for example, infinity over infinity would be indeterminate also, right? That would also be. There's one other example, more work. So this top one, if I evaluate this at 3, I just get negative 2 over, what, negative 16. So what is that? 1/8? We're done, right? Okay, bottom one. What am I going to do with this guy? Okay, I'm going to have to, aren't I? Because this one gives us 0 over 0. That's indeterminate. So remember, I have to carry the limit notation with me because I haven't evaluated the limit yet, right? So this limit is equal to the limit of x minus 2 divided by the quantity x minus 2 times x plus 2 if I factor, right? Okay, what am I able to do here? Good. And so remember, what I'm actually doing is I'm trading my original function for a simpler one, which is 1 over x plus 2. What do those graphs look like? If I compare the graph of the rational function x minus 2 over x squared minus 4, if I compare that to the graph of 1 over x plus 2, they're the same, except, what's the one difference? Good, it fills in the hole. Good. They agree at all but one point. This fills in the point that was missing here, right? You see how useful that is, though. Remember, they're not the same function, but what did we do? Great trick. We just said if we want to know where the ant thinks he's going to step on this function, we can answer that by saying, well, where does he actually step on this function, right? Okay? Don't lose sight of that, what a good trick that is. It's just a strategy. So as x approaches 2, then we just get 1/4. Okay? Good. All right. Another one. How about how about one like this? What if we did what happens if I try to evaluate directly? Indeterminate, yeah, so more work. Okay, what does the more work look like here? Remember? I think we looked at one of these, didn't we, on Friday? What did we do?
So you do
The conjugate. Conjugate, right? And think what a conjugate means, going back to, I mean, it really would have been Honors Algebra 2 is when you would have seen this the first time. You would have seen it last year also. Remember, all a conjugate is, conjugates are of the form A plus B and A minus B, right? Where A is the first term and B is the second term. So this is, so for example, this is A and that's B, right? And remember that the whole point of this, and this is a great strategy, but don't lose sight of kind of why we're doing this. We're doing this because the part that's really problematic here is that square root, right? That complicates the algebra. We're trying to trade an expression that has a 0 at 3 involving a square root for an expression involving a square root somewhere else that's not going to be a 0, right? So to get rid of that square root, the trick is we're going to multiply top and bottom by its conjugate. Okay, if we do that, what are we going to get on the top? Minus 4. Good. So first term squared undoes the radical. Good. So we get x plus 1 minus second term squared is 4 all over x minus 3 times square root x plus 1 plus 2. Okay. That's supposed to be, no terrible writing here, that's supposed to be an x plus 1. Let's fix that. So what's the top become if I simplify? Aha. Okay, and if I take my limit, which means evaluate the limit now, looks at x is approaching 3. After canceling the x minus 3's, that removes that indeterminacy, right? That's where we got the 0. Those were the factors giving us 0 top and bottom. And now if I take my limit, what do I get? Yeah, so square root of 4 is 2 plus 2, so 1/4?
Yeah.
Figured. Okay, good. Okay, last kind. So those are two of the analytical types that we typically run into. And here's the third, something like this. So limit of, how about 1 over 2 plus x minus 1/2 all divided by x as x goes to 0. Okay, what do you suppose happens if I evaluate directly? Be more work, wouldn't it? Because I'm going to get a 0 on the top too, right? Okay, so it's a more work kind. Now, what do you think if we have a limit of a function that involves complex fractions, meaning fractions of fractions, right? So if I break this into one big fraction, in the top, I've got fractions, an expression involving other fractions, and in the bottom, I could write that as a fraction if I wanted to. What do you suppose we do here? Multiply by the top and bottom by the reciprocal of what?
Like if you did the reciprocal, like the reciprocal times the top by the reciprocal bottom.
By the bottom flipped. Remember, we have to do the same thing to top and bottom, though, don't we? Right? We have to multiply by 1.
Oh.
So we can't change. We don't want to change the function. We're just going to do algebra to change its form. Right? Okay, good. So the answer is we're just going to simplify this, right? Now, what's our rule? If we go all the way back to like Honors Algebra 2, what's our rule for solving a complex fraction. Real simple. What do we do here? There are implied parentheses around the whole numerator and denominator. So if we follow order of operations, the outer parentheses would just be numerator, denominator. So we're just going to simplify the entire numerator into one fraction, right? Simplify the bottom into one fraction, already done in this case, and then flip and multiply by the bottom, right? So in the top, we've got to combine those fractions with the common denominator, right? So what's that look like? Well, what's our common denominator going to be?
2 plus x minus.
Okay, so the product of the two denominators, right? 2 times the quantity 2 plus x, okay? So then that means I'm going to multiply, well, here, I'll rewrite this now, so. So I'm going to have 1 over 2 plus x. Got to multiply, thank you. So we got to multiply the first one by what, Dib?
2 over 2.
2 over 2, good. 2 over 2. All right. Minus 1/2 times what? X plus 2 divided by itself. We didn't do anything crazy, we just multiplied stuff by 1, which doesn't change its value. And then on the bottom, we've got our x over 1. So what's that give us? On the top, we're going to end up getting a common denominator of 2 times 2 plus x, or x plus 2, whatever you want to say, right? And then we're just going to combine everything, all the numerators, right? What's that going to give us? I'm going to get 2 minus the quantity x plus 2. Agreed? All over x over 1. If I distribute the negative sign, would you agree that the 2's are going to cancel? So I'm going to end up with the limit of negative x over 2 times the quantity 2 plus x, or x plus 2, all divided by x over 1, right? I succeeded in creating one big fraction on the top and one fraction on the bottom. So now I'll just flip and multiply by the bottom, right? So that's going to give us the limit of negative x over 2 times x plus 2 times reciprocal of the bottom is 1 over x. We multiply straight across, and so what can we do here? When I'm multiplying fractions, would you agree I can just cancel like factors top and bottom? So I can do this. Everybody agree? Leaving me with the limit of, on the top I've got a negative 1, on the bottom I've got 2 times x plus 2. Now as x goes to 0, what do I get? Okay? Makes sense? Back. All right. Okay, makes sense? So we got those 3 techniques for solving analytically. That's about it for now. I'm going to leave it at that for today. Okay? Why don't you guys, we have a little time, right? 15 minutes or so, something like that? Okay, why don't you grab a Chromebook, jump into the Math Excel, and just kind of familiarize yourself a little bit.